So this is the 2022 paper 2 H446 exam. So let's get on it. So you might want to pause this to read it because I'm not going to read it out loud for every time. So you might want to pause and read this. And then essentially state what is meant by the term abstraction. Describe how Kira has used abstraction in her design of the tree. Well, it's for a computer game and these are the moves. So let's define abstraction. Abstraction is the removal of unnecessary details to make a problem easier to solve. Right, and here, Kira has removed, has labelled the moves with letters, and this gives us no information. And then I'll probably put something out. There are no details about each move, such as time it takes, etc. You could also put, for a fourth one, the move choices are also denoted by lines. So not like any actual understanding of how they might move on to anything else. And that should be fine. Okay, so now it says state why the tree shown in figure 1 is not an example of a binary search tree. Well, it's not an example of a binary search tree for two reasons. One, it has more than two nodes attached to a node, and binary means two, so we know that. Also, F is to the left of C, when in a binary search tree, C would be here and F would be here. So that's your two options. More than two leaves from a parent. Nodes, I'll put, sorry, from a parent. And, is it J? F is also in the incorrect position of being on the left of C. There we go. Let's go to this one. State what type of pointers are used to store nodes I, F, J, and H. So do not point to any other nodes, or that's just null pointers. Okay, easy peasy. All right, so this question here wants to evaluate a breadth first traversal. So of course you would visit the head node A. Good writing. And then it would go BCE. Is it B, C, and then E? Then it's going to be D, F, G, H. D, F, G, H, and then the last ones were I, then J. Right, that's that done. Right, describe the steps an algorithm would follow to delete node E from the tree. Alright, so let's have a look at the tree again. So first step is to find E, and then we've got to remember where we came from and point A to H, and then delete E. So first step is to find the node E and remember what its parent was. Once E is located, we link the parent node to the child node of E. And then delete E from memory if required. Found. We link the parent node to the child of node E. Yeah, that's pretty much the steps. Not too bad. Right. The move represented by the node K needs to be added. Node K needs to be joined to node E. Describe the steps it will need to add node K to the right of node G. So you need to find node G, then create node K, because we probably haven't got node K, then link node G child right to, one of them is no right, it's not a binary search tree, to node K. Yeah, that should be pretty much it. Right, so Kira could use a graph data structure to represent the moves in the game. Give two similarities and two differences. So similarities, they both use nodes, and they both have links called edges. Okay, so difference is that a tree has a root node, whereas graph does not, and a graph is bidirectional, whereas a tree is unidirectional. So there we go. Yeah, that should be enough. There's others, but they're the main ones. So what's the good thing about decomposition, basically, is what this question is saying here. I'm not going to read it out because you can pause. But basically, decomposition makes a problem easier to solve. Simply, really. Does it say what is decomposition? No, I might say it anyway, just for, you know. Decomposition is breaking down a problem into smaller parts, just in case. Why is it good? Well, it makes it easier to solve. Might be able to reuse code in another place, make a library, something like that. What else? People can specialize in certain areas, such as networking. I mean, there's quite a lot you could do here. Easier to debug. The error is likely in that place. Yeah, there's lots of things you can do with that one. Okay, so discuss the need for concurrent processing in OCR's ticket system and the benefits and drawbacks of this. So it's a ticket software development company that sends online events. So obviously they want to better sell to more than one person at the same time. So let's explain what concurrent processing means. That tasks or threads can overlap each other and be performed at the same time. In this instance, it would mean that the system can sell two tickets, the same event, to different people simultaneously. Right. Let's get that sorted. So that's obviously very useful. So there's my knowledge. There's my application. Now my evaluation. This is good because in real world situations, tickets often sell fast upon release and people will not wait to purchase them. There you go. So that's my application. The program will need to block requests to records that are currently in use. This can be done with record locking, as two people could be attempting to purchase the same seat. That, if it was to be allowed to happen. This is generally good, but with record locking, you must take care in case you get deadlock, where A is waiting for B to finish and B is waiting for A to finish. They share, they both have data, other wants to change, something like that. I don't think I wrote that brilliantly, but with record locking, you need to be waiting for B to finish and B to finish. Yes, that's quite a good little second section. Programming a more complex system like this will cost more money and time. OCR, is it OCR tickets? What's it called? OCR-tickets will need to spend more money and wait for the software to finish creation before using it. Which could cause a loss of profit. This would still, overall, be a good idea. In the future, more purchases can be made, recouping any losses. Something like that. There are definitely other things you could have written about, complex programming. There's lots of stuff you could write for this one, but it's only 9 marks, and that's typed, so that's actually quite a lot of written work. I think that's more than enough for this question. Right, so I've set this question up a bit weird, but basically we've got a Tracy algorithm like this. And I've set all this up to make it a bit easier. Probably this is enough, actually. I don't really need this, probably. But there we go. Anyway, so let's get this sorted. So we're running it with these numbers 0, 7, 35. So the array goes there. Num1 is 0, num2 is 7, num3 is 35. 0, 7, 35. Result equals 0 plus 7 minus 0 divided by 2. Well, 7 minus 0 is 7, divided by 2 is 3. So it's 0 plus 3, which is 3. Okay. Is num2 less than num1? No. If the array result, so the array result is 3, this one here, is less than num3, which it is, then we return this. So now we've got to do this. I'm just going to put enter there to push that down. Get rid of that. The array result plus 1. So I'm going to run this again. I'll select that because that's not there. The array, comma, result plus 1, comma num2, comma num3. So result equals num1 plus num2 minus num1. So num2 minus num1 is 3. Okay. Num2 minus 1 is 3. Divided by 2 is 1 because it rounds down, plus 4. So the result is 5. Okay. So if the result 5 is less than num3, well, sorry, is num2 less than num1? Yes. No, sorry, it's not less than num1. If array result is less than num3, so the result is 5, so 0, 1, 2, 3, 4, 5, even though it's labelled at the top. Is that less than num3? It is less than num3, so now we've got to do this one again. So, but this time its result plus 1 is going to be 6. Okay. Yeah, 6, 7, 35. Because result plus 1. So then num1 equals 6, num2 equals 7, 3 equals 35. Result equals num1 plus num2, that's 1 divided by 2. So 7 minus 6 divided by 2 is going to be 0. So this is going to be output as 6. Okay. If num2 is less than num1, so minus 1, it's not. If the array of the result, so what's in array 6, that's 35, is that less than num3? No. So that's not true. Okay. So then we go here. Else, if the result is bigger than num3, no, it isn't, because it's equal to num3. So we don't do that one. Else return result. So it's going to return the result, which is 6. And there you go. So that wasn't too bad. A bit fiddly, but there you go. And here, the algorithm is performing. Well, the tip is that this data is in numerical order, ascending order. So, it's obviously searching for something. So if you look here, this is mid plus 1, this is mid minus 1 kind of thing, isn't it? This is low, this is the high, so it's obviously low and high. So this is a binary search. Okay. There you go. That's that one done. Now we need to compare differences between recursion and iteration. 2 differences. So recursion uses more memory as each method called will add data to the stack. Iteration will use less memory. Was terribly put. Recursion often creates elegant code, whilst iterative solutions can be longer. Something like that, but I hate recursion, so let's just ignore it. Anyway, right, let's go on to the next one. Why is it printing the recursive function again? Rewrite this function so it uses iteration instead of recursion. All right, cool. Let's copy this here. And it's binary search, so we should all be able to do binary search because it's like a key thing that we've studied. But let's move that over. I'll write it in the same way they did it. Function the array, comma num1, comma num2, comma num3. And I'm going to write it in a way that makes it easy to understand rather than being necessarily the best, because this, when you get a real exam, it might not be this function you're creating. But when you've got to turn a recursive function into an iterative solution, one of the first things you've got to look at, what is the get out clause? Well, they're all get out clauses here, but actually, well, this one here and this one here. So, so basically, while num2 is greater than or equal to num1, so I'm doing the opposite because I'll just use Python style code because it's easier. So basically loop while that's true, so the opposite of this, and then at the end obviously here I'll do return -1. I don't know why it's done a massive thing, so I think I'll just do that. I think that's tabbed there. Anyway, so obviously we need to then get results. So result equals num1 plus num2 minus num1. It's double slash in Python for that. You could have put div, be fine. Result. Okay, so now we've got to look at the solutions. If the array result, no, I think we need to check if it's true or not. No, I'll do it the same way. The array result is less than num3, then we just move the pointers. So now num1 equals result plus 1. If the array result is greater than num3, then num2 equals result -1. Else turn result. And that should be it, really. There you go. Because when it runs itself, we're essentially just altering the variables. It's actually really easy once turned into a non-recursive method, because all the recursion does is just change these variables and then run it again. It doesn't do anything really major that can't be done quite elegantly with an iterative solution. But yeah, that's pretty much it. Well, I just tested this to see if it worked in Python, and it did, but only after I fixed my numerous errors of typing. But that's what you get. So that should be num1, and that should be num1 there, and that should be num1 there. But apart from that, it was all perfect. Anyway, it worked and is correct. So that's that. And then move on. So here it says, explain why data array is passed by reference and not by value. So passing by reference will mean that any changes that happen to the passed value data will actually be permanent, as data array will point to the same memory location. So that's what it means. Just to be clear, all arrays are sent by reference, so this is completely pointless to send it by reference, because arrays are always sent by reference in all programming languages, because sending in a copy of array would be really slow. So in essence, this is pointless. But yeah. Anyway, we will carry on. But yes, here we do it because this is a sort, so we want to permanently sort the data in the array. The alternative is to return the sorted array. Something like that would be fine. State whether it's ascending or descending. So this is, I mean, it's very likely to be descending because ascending is the normal. So let's look. So for I equals 1, so it starts at 1 to the length, temp equals data I, temp position is I, so it's I is at 0, data away is at 1. X equals false, while temp position and X equals false. So while the position is greater than 0 and X is false, if the data array temp is less than temp, yeah, so if it's less here, then we're doing a swap. Okay, so if the data in temp position is less than the temp value, which is the one here, but this one's on the left, don't forget. So it's going to swap, then temp plus 1 equals data array temp position. Yeah, so it's going to put the higher one in. Yes, it's going to swap the higher one first because it's saying if it's less than, then we swap them basically. So it's going to go, yeah, basically it's an obvious answer. If it's less than, swap them. So descending as the program line 07 checks if the data array temp pos is less than temp. If it is, it will swap the values, putting the higher value on the left side, making it descending. Anyway, here we go. Something like that will do. Let's go on to the next one. Now, I started to write this on the video live, but it was taking so long, and I thought, oh, it's just long. So basically here, you're asked to compare two other sorting algorithms of merge and quick sort. Compare the use of merge, quick, and insertion sort on an array with small number of elements and on one with a large number of elements. Make reference to the time and space complexity, basically, of each algorithm using the O notation in your answer. It doesn't say space notation, actually, but I will talk about it anyway, because why not? So first of all, how do I answer this? Well, I always think, explain this. So I start off by explaining what the big O notation means, and it is of course the relationship between the number of values and the memory usage or time taken to complete the algorithm. So it's a relationship. It's not necessarily, it doesn't tell you how fast they are, it tells you how fast they are compared to how many elements there are. Now, so I explained that, and you can obviously read that by pausing the video. Nothing too interesting there. And then I go through each different one, evaluating each one. So quick sort, I mean, you can read it, it's nothing too crazy, but I go through each one, talking about it in terms of smaller data set, large data set. I do talk about space as well, even though it only says time, but big O is to do with space as well. And then I talk about merge sort, insertion sort, and then of course I make a decision about which one I would choose for different data sets. So that's how I structure out that question. Obviously you can read it, I can pause it like this, so you can read this bit, and then I can obviously pause it here like this to read the rest. So I'm not going to go through it any more than that because obviously it's a long question and it's boring on the video. So this is just the rest of the stuff. So let's do the last question in this section, and I'll probably do 2 parts, so this will be the last part. A full sorting algorithm is a bubble sort. Describe how a bubble sort will sort an array of 10 elements. Well, a bubble sort works by comparing pairs of values together and swapping them if they are in the wrong order. It goes along the array looking at positions 0 to 8 as it will compare to the next position, so we don't go to 9. So as I look at positions 0 to 8 as it will compare to the position of 9. Once it reaches the end, swapping them if required, this is called one cycle. But it does not mean that the data is sorted. We must repeat cycles until we get through a whole cycle and there was no swap. Now I actually, as an extra thing here, and just because it's 6 marks, I'm actually going to write out the code for bubble sort, which is quite easy in Python. So for I'm just going to do while true. I'm going to do, actually, I'll do the proper 1, 2, 3, 4. I'll do swap equals true. While swap. So while this is true, we did a swap. Now I'm going to set swap to false because I'll copy that actually. In fact, I'll put one more in there. That didn't work at all. Anyway, so I'm now going to loop through it for I in range length of data -1, because in Python, if there was 9 items in there, it would go 0 to 8, but we want to go 0 to 7. Sorry, if there's 10 items, it would go 0 to 9, but we want to go 0 to 8, so I'll do -1. If data I is greater than data I plus 1, then we need to swap them. Now, I won't use the fancy Python way of swapping them. I'll just take a copy of data I, plus 1, sorry, data I plus 1 equals data I, and data I equals data I plus 1. Swap them, and then I'm going to write swap equals true. And that is actually all you need to do. We just loop through, keep doing this. This for when this doesn't do a swap, it will of course fall through. So that will actually do it. There is a slight improvement you can make by reducing this number every time, because each cycle puts the biggest number into the correct spot. But that's perfectly fine. So I'll just stop there.